So we were saying that in phase 2, we can determine the equation of velocity. We said that the velocity in this phase is equal to minus 2t plus constant. And when we applied the boundary condition that at t equal 10, v is equal to 100, we found out that this constant is equal to 120. So the velocity is minus 2t plus 120. And then to determine the value of t prime, we said we can use the condition that we know that v at t prime is equal to 0. And then all we have to do is to apply this condition and say that 0 is equal to minus 2t prime plus 120. And then we obtained exactly the same result as in the graphical method. We obtained that t prime is equal to 60. Okay, so both graphical and analytical methods will lead to the same result. Now, you will see that with practice, the graphical method will become very simple for you, and sometimes it can help you into getting your result in a fast way. Okay, now the last question is to determine how far has the car traveled. We will see together that graphically it's much easier to determine the total distance. So I will go back now to the graphical method. From the graphical method, we were able to draw v function of time. Can you just tell me the total distance traveled represents what graphically? Who can tell me how we can deduce the total distance traveled from the graph?
From this graph or from the velocity graph?
From the graph of velocity with respect to time. So we have
area.
Very good. Time. The area, very good. So you can see here that this question is much easier to solve using the graphical method, because they just want me to find what is the total distance traveled by the car. So how far has the car traveled from the original point? Here, there is no change in direction in my problem. The velocity is always positive. So I'm moving along one sense to the right. Let's say if the positive direction is to the right. Okay, so I'm moving to the right all the time. So the total distance here is equal to delta s. Okay, and we know that delta s is integral v dt. So I can say that the area under this graph is the total distance traveled. So the graphical method here will be easier than the analytical one, because all I have to do is, I know already that the velocity here is 100. And I know that t prime here is 60. So here I have 60 seconds. And to determine the area of this triangle, all I have to do is to say that for a triangle, the area is height times base over 2. So in a very fast way, I can say that the total distance here is equal to the displacement, because as I told you, delta s here is positive and no change in sense. So the distance traveled will be equal to delta s, will be equal to the area under the graph, which is 100 times 60 over 2, which is 3000. So you see how it's fast here. If you want to use the analytical method, it will take more time to solve for the total distance. So the total distance is 3000 meters. Now, if I want to use the analytical way, okay, I should first determine what is the distance traveled in phase 1, and I should add to it the distance traveled in phase 2. Okay, And this will take more time than doing the graphical method. Let us do it. So we know already the expression of velocity in phase one. So we can say that in phase one, the velocity is equal to 10t. So if I integrate this function, I get that s is 5t squared plus a constant, okay? And I can consider that at t equals 0, the particle was at the origin, so my constant will be equal to 0, okay? So now I can say that during phase 1, what is d1? So distance moved in phase 1 is equal to delta s of phase 1, because delta s is positive and no change in sense, equals to, at the end of phase 1, the time is equal to 10 seconds. So it's 5 times 100. So I traveled in phase 1 500 meters. Okay. Now, in phase 2, what is the equation? We got together that the equation of velocity is minus 2t plus 120. Okay, so I can say that if I integrate now, look, let us do here the method of separation of variables to practice on another method. So this is ds by dt, okay? This is ds by dt. So to do separation of variables, I will take dt to this side, and then I can write that ds is equal to minus 2t plus 120 dt. And now I will integrate for both sides. Okay. Now what will be the extremities of my integral? I should consider the beginning and the end of phase 2. Okay. I know that for time, phase 2 will start at 10 seconds and it will end at 60 seconds. So I should integrate here between 10 and 60. Okay. While for ds here, at 10 seconds, the position s correspond to the end of phase 1, which is 500 meters. So I should integrate between 500 and s2. S2 or s final, if you want, is the final position s, which represents then the total distance. So S final will represent the total distance traveled, because d total is equal to delta S total, which is S final minus S0. And since I considered that initially I am at the origin, so S0 is 0, and the distance traveled will be equal to the value of S final. Okay, so from this analysis here, you get S final minus 500. When you do S final minus 500, you will get D2, the distance moved in phase 2, okay? Equal to, by just performing this integration here, if you integrate, you have a minus 2t integral is minus t squared. And for 120, it's a constant, so plus 120t. You apply this between your boundaries, which are 10 and 60. And you will get, if you do the calculation, you will get 2,500. So distance moved in phase 2 is 2,500. If you add to it plus 500, you get that S final is 3,000, which is exactly the same result of the graphical method. But you can see here that the graphical method is much faster. You were able in one simple equation to get the result. While for the analytical method, we had to do several steps. So sometimes the analytical way is easier, but also other times the graphical way is easier. So try to select always the shortest method to save time. Any question?
Yes, Professor.
Yes.
In the graphical method, if we have a negative part,
Yeah.
we add the both area.
If you want to get a distance, you take the absolute value. Yes. Okay. Yeah. For example, if you have this graph of velocity, and I asked you what is the total distance traveled, then you should consider at any phase the absolute value of delta S. So this is an example. If you have this, okay, and I ask you what is the total distance traveled. So this is V function of time, okay. You say that this part is above the t-axis. This means that delta S here is positive, okay. And then the distance traveled in this phase is equal to the value of delta S1. So D1 will be equal to delta S1 will be equal to this area 1. Okay. Now, for the second part here, which is below the axis, you consider that delta S2 is negative. So delta S2 will be negative equal to minus area 2. Okay. But if you are calculating the distance, if you are calculating the distance D2, you take the absolute value of delta S2, which is plus A2. Okay. So here, the total distance will be different from the total displacement. Okay. Because if you want to calculate the total distance, you will say that for this graph, D total equals to A1 plus A2, while for the total displacement, okay, delta S total will be delta S1 plus delta S2 will be equal to A1 minus A2. Okay.
This is for the position, yeah.
Yeah, exactly. So it will be A1 minus A2 to get the final position. Exactly. Okay.
Okay, thank you.
Any other question? Eli, are you asking a question, or I didn't understand what do you mean here? Any other question on this? Okay. Now, if you want to plot the graph of position with respect to time, okay, you can do it or analytically. So already analytically, we found together the function, how S is varying with time. Okay, you can plot them. And now, if you want to use graphical method to plot S, look what we can do. So we go back to the velocity graph. For the velocity graph, I have two linear variations. In phase 1, it's increasing. In phase 2, it's decreasing. Okay. And I know that here it's 100. Here the time is 10 seconds. And here the time is 60. Okay. So if I want to draw graphically, if I want to deduce graphically the graph of S, so this is S function of time. I can do this. First, I say that the velocity represents the slope of S. So since here my velocity started with 0, so I will start by a 0 slope or horizontal tangent for my S graph. Okay. Now, I know that from my calculation before that the value of S at 10 seconds is 500. I can verify this graphically. Okay, if I want to find what is S at 10 seconds, all I have to say is that delta S between 0 and 10 is equal to this area. Okay, and this area is equal to, since it's a triangle, it's 100 times 10 over 2. So here I just put area 1 equal to 100 times 10 over 2 equals to 500, which is expected because we have demonstrated together that delta S in phase 1 is 500 meters. And since I'm starting from 0, so I can say that at 10 seconds, the value of S will be just 500. So let me put it here to be on scale a little bit. So let's say this is 500 meters. Now, all I have to do is to join these points, but I should pay attention for the profile. Since V is linear, S is second degree. And to know how the slope is varying, I can just look at V. V is increasing. So my slope is increasing with time, okay? And it will reach at 500, the slope at 500 will be equal to the value of velocity, which is 100. So I can just put a small note here that the slope at this point is equal to 100. And then I can relate my points to get the graph in phase 1. It's a second degree parabola because V is linear. So I can just say that this is a second degree parabola. And this is enough as graphical presentation. I know the profile, I know the slope at different points, and I know the extreme values. Now, in second phase, what will happen in second phase is that the slope will change behavior. Now it will start to decrease. Can you tell me, do you know what is this point? What do we name this point here? When the slope is increasing and then it will decrease, the point between the two
Maximum.
zones. No.
Inflection.
Inflection, very good. Inflection point, okay? At the inflection point, I have sudden change in slope profile. So it was increasing, now it will decrease. So this will lead to a change in curvature. Your second degree here, parabola is concave up. It has an upward concavity. While in your second zone, the slope will decrease and it will end up by a zero slope at 60 seconds. So at 60 seconds, okay, you'll end up with a slope of 0. So you in phase 2, your parabola is characterized by a downward concavity. So this will be your profile. Your slope will decrease until reaching nearly 0. So you just have to join these points and you get your graph. Okay, now you can just put that the slope at this point is equal to 0. And this is a second degree parabola, but as you can see, the concavity is downward. And just you need to determine the value here, the final value here. We already determined this value by saying that you have two methods to determine this value. Or you say it's the total area as we did before, which is equal to 3000. Or you say that in phase 2, the change in delta S, so delta S2 between 500 and the final point, so this is delta S2, is equal to the area under the graph for the second phase. So this area here, this one, okay? And area 2 can be calculated as the area of a triangle. It's 100, you know, the height is 100. The base is 60 minus 10, so it's 50 over 2. So you get 2,500. So A2 is equal to 2,500. This represents delta S. And since S at the end of phase 1 which is S at the beginning of phase 2 is 500. I should add to 500 2,500 to get S final, which will be equal to the value of 3,000. Okay. Any question on this?
Yes, doctor.
The graph, look, the graph should be يعني as much as possible to scale. مش 100%، يعني مش ضروري انه 100%, but at least should be a little bit representative. Okay.
Doctor.
Yeah.
As I know السكن بيكون شكلها إنه بتبلش مثل ما أنت عملية بعدين بتكمل لفوق، مش إنه بترجع it concaves the other way.
No, it's not true. انت من ليش يعني يعني what you are basing on to say انه بتكمل طلوع. It's not right. Because look, you can do the interpretation in several ways. The acceleration is second derivative of position. When your second derivative is positive, the concavity is upward. When your second derivative is negative, the concavity is downward. So if you do the interpretation of A or you do the interpretation of V, both will tell you that in phase 1 you have an upward concavity and in phase 2 you have a downward concavity. I don't know what you are talking about. Maybe you are talking about another example.
No, هلا it was clear. Okay, that's one phase. هلا كمان it's two.
Okay. Other questions? Okay, so let us do another problem. Okay, here in this problem, they gave us the VS graph describing the motion of a motor as shown. Construct the AS graph of motion and determine the time needed for the motor to reach position 120 meters. So in any problem, you can think about two approaches. Here, since V is given function of S, it is easier to work with the analytical method. And already, okay, you have simple functions. So you can, even if they don't give you the function, you can find them. So in phase 1, you can say that V is linear with respect to S. And I already have 2 points. I know that at S equals 0, V equal to 3, and at S equals 60, V equal to 15. So I can say that this linear variation can be written as V equal to a certain slope that I will call, let's say, constant slope C times S plus a constant B. To find the slope, all I have to do is to apply delta V over delta S between the 2 points here, because it's a linear variation. So I can find that the slope of this line is 15 minus 3, which is 12, okay, over delta S, which is 60 minus 0. So I get that the slope is 0.2. And now to get my value of constant B, I have to replace the coordinates or of 0.1 or of 0.2. If I take 0.1, I can say that for S equals 0, V equals 3, and this is equal to B, because if you replace S by 0 here, you'll get V equal to B equal to 3. So from here, you can determine the variation of V with S in first phase. Now in the second phase, V is constant, so it's just equal to 50. Now, what they want me to find is first to determine the graph AS, okay? So all I have to do is to write the relation between A, V, and S. I know that A is V times dV by ds, okay? So all I have to do is first to calculate what is dV by ds. Since I have here the expression of velocity with respect to position, I should derive it. If you derive it, you get 0.2. So dv by ds is a constant equal to 0.2. So I can say that in phase one, the acceleration is equal to the function of velocity, and I multiply it by 0.2. So it's 0.04s plus 3 times 0.2, so plus 0.6. So this is the equation of acceleration in phase one. It's a linear variation with position. Okay, so please pay attention here. V is linear with respect to us, and also A is linear with respect to us. Not like time. If V is linear with respect to time, A is second degree function of time. But if V is linear with respect to time, dV by ds will be a constant, so A will also be linear with respect to position. Okay, sorry, I said V with respect to position constant. Okay, so when V is linear with respect to us, A also is linear with respect to us. Okay, but with respect to time, it's not the case. Now, in phase two, what do I have? In phase two, I have constant velocity. V is constant. So no need to do any calculation, because when V is constant, A is 0. And you can deduce this if you go to this expression, because dV by ds will be 0 when V is constant. So A will also be then 0. Okay.
Professor,
Yes.
in the expression of A in phase one, I didn't really understand why you multiplied by 0.2.
Okay, because if you go back to the definition, you have that ADS equals to VDV, okay? And what you want to find is A. So you can write that A is equal to velocity times derivative of velocity with respect to position, okay? Let us replace now. What do we know about V? We know that V is equal to 0. So I will replace V by 0.2 as plus 3. Okay, I should multiply this function by what? I should multiply by derivative of V with respect to us. Derive this function with respect to us. What do you get?
0.2.
Exactly. So all you have to do to find A is to multiply the function V by the derivative of V with respect to us, which is 0.2. Okay.
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 Thank you.
So now, welcome. Now we know the equations in both phases, so we can construct a function of s. So we have in the first phase that a equation is 0.04s plus 0.6. This is a linear variation, so we can just plot it. It starts at s equals 0, A is 0.6, so it will start from here. And the slope is 0.04. It's a very small slope. So like this, let's say. And it will end by the value of acceleration at the end of this phase can be determined by replacing s by 60. Okay, so if you replace s by 60 here, you can get the value of acceleration at the end of phase one. Okay, so here you just have to say it's 0.04 times 60 plus 0.6. Okay, so you have 0. So 0 and 0 will cancel out. 0.4 times 6, so you have 2.4. So 2.4 plus 0.6, it's 3. Okay. So the acceleration at this point is 3, equal to 3. And then suddenly it will drop to 0. Okay. So here it's not a lot to scale, but pay attention to at least be to scale بالبure figure, okay? And now at the end of phase 2, we have a drastic decrease, sudden decrease to an acceleration of 0. So this is a graph of acceleration with respect to position, okay? Now, they also want us to find the total time needed for the motor to reach a certain position, which is 120 meters, okay? So here we want to relate with time. What do you suggest to do to relate with time? What should we do? Which relation you will use?
We can
Okay.
use,
Yeah,
we have V.
exactly. We have V function of S, and we know that V is ds by dt.
PT.
Okay, so we should find, if you want, the time of phase 1 and add to it the time of phase 2. Okay, so in phase 1 we know that velocity is equal to 0.2 s plus 3, which is ds by dt. Okay, and then we can do separation of variables. Here pay attention, since v is function of s, we'll take it from the side of s. Okay, so we have ds over 0.2 s plus 3 is equal to dt. And now to find the total time of phase 1, you will integrate for phase 1 between 0 and t1. Okay, and from the other side you'll integrate between what and what? What are the extremities of s for phase 1?
From 0 to 60.
0 to 60.
Very good. So from 0 to 60. Your calculator can give you this integral. Okay, then you can find the time t1 of phase 1. So you get t1 from this equation. Okay, and t1 will be the boundary condition for phase 2. And now for phase 2, okay, you write that v equal ds by dt equal to 15. Okay, for phase 2 it's much easier because the velocity is constant. So you can say that delta s of phase 2 is equal to 15 times delta t. And what is delta t of phase 2? What is this delta t of phase 2? It's the total time minus what? Minus t1 of phase 1. Okay, so
T1.
yeah, exactly. So delta s2 represent the displacement in phase 2, which is 120 minus 60. So you can write that 60 is equal to 15 times the total time t final, okay, minus t1. So t final will represent for you the total time of motion, and this is what we want to get. Okay, so in this way we'll be able to find the total time needed to reach position 120 meters. Any question on this?
Thank you,
But
Professor.
Professor, to make sure you
Yeah.
added up the delta t's, right?
Look, delta t, delta t1 هي التايم of phase 1. Okay, delta t2 هي the time of phase 2. طب delta t2 represents what? It says, so if I illustrate this on a figure, okay, delta t1 will give you the time of phase 1. Delta t2 will give you the time of phase 2. T final is the summation of both. But if I replace directly delta t2 by its expression اللي هي t final minus t1, then I get directly t final. Okay,
Perfect, thank you.
يعني فيك إذا بدك تجيب أنت أول شيء delta t2 calculation ترجع تقول إنه t final is the summation of both, or you can directly say, I know that T final is delta T1 plus delta T2, so I can replace delta T2 in my equation here by the total
Dotted?
time minus T1, and you get T final. So both approach will give you the same result. Yes. Yes, who are asking a question? Any other question on this?
I have a question, Professor.
Yeah, tell me.
You told us to calculate the integral using a calculator, so you don't need to see ln أو هذا بس you want the final answer.
Exactly. Look, yes, I already told you, when you don't need the function for other parts, it's fine for me to use the calculator, okay?
Okay, thank you.
Other questions?
All clear.
Okay, thank you. See you next time. Bye bye.
Have a nice day.
Thank you.
You too, bye.